I know. You're always cold, so.
Because I'm next to like a windy door.
Is it colder or
No, when the
War-
wind comes
is
through,
it warm?
feels nice.
Yeah, pretty nice.
okay? So
Now you're gonna be more parents.
Yeah.
no more parents. Okay, this limit as x approaches a.
Yes.
Yes. Okay.
You didn't press record.
Yes, I did. We're already 36 seconds in. Looks like it.
It's not changed, but it's a change.
Oh, it's changed on mine. You know what? I think the internet is not working great.
Classic community.
We don't know.
Oh yeah. Yeah, whatever.
There you go. So I want you to find the derivative. So in other words, I want you to find f prime of a using this formula.
What's A?
We don't know what a is. So basically what I'm saying is come up with a formula for any value of a that will represent the derivative of y equals square root of 2x. Okay? So we did something like this on the homework. Here, I'll walk you through the first one, then I'll give you another one to try as an example. So I want to find f prime of a. So that's going to be the limit as x approaches a. Now f of x, what is f of x? That's just our function. That's square root of 2x minus f of a. So that's just square root of 2a all over x minus a. Let me just pause there, make sure. Yeah, exactly. We're just rewriting it with an a.
And now we multiply by the conjugate.
Right, so I can't plug in, I can't do the limit because if I try, it's going to make the denominator equal to 0. So we talked about in the notes when we had a square root, even though it's not in the bottom, we want to try to simplify this, okay? So I'm going to multiply by the conjugate of the top, so that's going to be square root of 2x plus square root of 2a over square root of 2x plus square root of 2a. So what does that give us? So it just gives us a 2x minus 2a. Now do not distribute or multiply out the denominator. Because remember, maybe you remember that I said our goal is to get rid of the x minus a on the bottom. So take a look at the numerator. What can I do in the numerator? All right, so I'm going to factor out a 2.
We didn't say that. Oh, and Sean. Oh.
And I get x minus a. And that's perfect because, well, it is cool. Why is it cool, Rowie?
Then you can just cancel them out, and then you get the chilio.
And what would the chilio be?
2 over radical 2x plus radical 2a.
All right, but now can I take the limit?
Heck yeah.
Okay, so by taking the limit, I mean replace all my x's with a's. So I have 2 over square root of 2a plus square root of 2a. So look at that. We have like terms. I can combine them. So I have 2 over 2. Because the 2's will cancel. So I have 1 over square root of 2a.
That's so chill.
All that work, but it worked out nicely. We were able to cancel. We were able to plug in. That's all we could do. Now, don't try to rationalize. Okay, remember, we don't care about radicals in the bottom anymore. It's fine to have radicals in the bottom. And in fact, this time we tried to get rid of the radical in the top, which is opposite of what we've done in the past. Now, let's say my next follow-up question, using that same equation, that same function, what if I said, what's f prime of 8? And then a follow-up question to that is, what's the equation of the tangent line?
We use the same equation.
Yeah, I'm going off of that the same equation that I started with.
Don't you plug 8 in for x or a?
Okay, so the derivative, even though I have an a here, remember we said f prime of a is 1 over square root of 2a.
Oh.
Or you could say f prime of x is 1 over square root of 2x.
So is f is 1 over 2.
So it's going to be 1 over square root of 2 times 8, which is 1 over 16 under the radical. So that's 1/4. And now how about our tangent line?
Y minus 4. Because if you plug 8.
Right, so if I plug 8 into the original equation, which was just square root of 2x, we get 4. So my x coordinate is 8. My y coordinate is 4. So, Max, what did you say the tangent line was?
Y minus 4 equals 1/4 times x minus 8.
Good?
You guys remind me who Lord is.
Yes. And what if I'm not going to write it down, but what if I had asked for the normal line? We would just change that to a -4 slope. Good. Yeah.
I had the sauce today, so you and your brother can find it.
Sorry, you made that fruit on purpose. Yeah, I accidentally went.
This house now.
Like, I know you wear shirts.
That took up nearly
got
half
that
my
shirt
page.
on
You need to
purpose.
make shorter crop. That took up
To be
my entire
super
family. Yeah.
I'll take that under consideration.
As you should.
Are you sure?
See this? Top page.
Yeah, but how many lines did you skip in between?
I want to be able to see what I'm doing. You can see what you're doing. I bet that took up half a page.
You see, if his
I actually think it took up-
I think it does to me.
It took more than half a page probably for me.
Yeah.
Like, so
Because I wrote every little step though, and I didn't work sideways, I just worked down.
on test, it's like 12 credits.
See, I used like pretty much a whole page. Oh, were you still writing or are you?
No. At least I think it was still working.
Not you.
I feel like we should get like extra pages on this test.
Listen, it's a take-home quiz. If
yeah.
you need scratch paper to write on, I'm giving you permission now so you don't have to email me. You can take out a piece of scratch paper when you're at home, okay?
I'll use a copy.
You have my permission.
I need scratch paper that's on my computer.
I'm not gonna
Website
give you
that can
scratch.
solve it.
What if I want to ask a question that you can't answer? Can I still email you?
Oh, were you still writing? No, okay.
Very good, very good.
I was worried.
Adam asked.
Okay.
Yeah, can I have Adam Ash do it for me?
No.
What about Walker?
What about me? 'Cause he's a junior.
Who's Adam Ash?
Can I have Walker do it?
Okay. At the end of the period, I was going to do some examples that would help. Like that example will help you on the quiz. Do we feel okay about that? Okay.
Can I have Walker do it?
So, no.
Can I let Bubba do it?
Can I have Aaron Drew do it?
No, it's due on Monday.
We have 3 days to do a quiz. We're good.
I'm going to get myself spit on it.
It's a lot longer than
Swanee's gonna do it the morning of. He's like, oh yeah, I forgot.
I'm
The bonus.
I'm pretty much walking you through a practice quiz right now. So,
Oh.
I don't have a practice quiz, so I figure where the function is differentiable. Sorry. That was supposed to just be differentiable. Okay. Find the values of x where the function is differentiable. So I'm going to give you a few different type. Okay?
Looks at take home quiz.
And then over odd is vertically flawed.
No, even over odd
Vertically flawed or
is a fraction that's a fraud. And odd over odd is just weird.
Just stop, please.
We love you, Roy. Just a little bit. It's not hurt. Yeah.
You're utterly lying.
I'm not utterly lying. How dare you?
Why are you guys isolating me?
It's a free country. Does that even
I didn't answer the question.
Oh, we're supposed to do these.
Okay. I just wrote down a few different examples. I'm going to add another one under this.
Right. Yeah.
Yeah, LN. Sorry.
Why?
Oh wait, how do you do that? Oh no. Yeah. Wait, how do you do that?
Okay. So,
Guys, check this out. Odd or even is pretty chill.
all right, here we go. The word differentiable, okay? I wrote down we talked about this yesterday. The first thing you should check for is continuity, all right? So, first, check for continuity. If it's not continuous, then those are the places where it's not differentiable, okay? After that, then we check for, I'm going to write down, cusp is what? That was even over odd, and then it was a vertical tangent was, and that's odd over odd, where the numerator in both situations is less than the denominator. Okay? Do I have to write that? Do you want me to write that?
Wait, so where it's not continuous is where it is not.
It's not differentiable. And then the corner is either when you have an absolute value, but really it's when you have a piecewise function, which an absolute value falls into that, where the derivative from the left is not the same as the derivative from the right. And I didn't quite have enough room on these, so I'm going to give you like 2 examples underneath this when we're done with these on piecewise functions, okay? All right, so what do we get for the first part?
1 over x plus 1.
So this is x plus 5, x plus 1. I don't cancel in these situations because it's a removable discontinuity still, so, right?
What if you just look at what you just
I don't care what's in the top. I don't care. I only care about what's in the denominator. So it's going to be differentiable where? From negative infinity, negative 5, and then, what? Where'd you get 3?
3 section.
Oh, okay.
Did it happen?
Okay. So differentiability, just remember, don't cancel. Next one. What do we see?
I see a
vertical tangent.
Vertical tangent. Where does the vertical tangent? This has a shift of. Okay, so 2, that moves it up. What does the 6 do? To the right. We really only care about horizontal shift. The fact that it moves it up and down doesn't really affect my intervals at all. Well, it doesn't. So
Are you insane?
it's going to be from negative infinity to 6, and then 6 to infinity. Good?
Sure.
What do we know? What do we know about the domain for logarithms? It has to be greater than 0. So x plus 2 must be greater than 0, so it's going to be from negative 2 to infinity. How about the next one?
Minus 1 to the 1/3.
Ah, so we could rewrite this as x minus 1 to the 3/2. What is that? Nothing.
Well, I mean, it is something, but it's not.
Okay, so.
Vertical tangent or.
Okay, so hold on a second. This does not fall under any category.
So it must be.
So what we need to figure out, so that means there's no discontinuities, there's no vertical tangent, there's no cusp, and there's no corner. So next we have to look at what's the domain. Yeah, Sean. So we need to make sure that what's underneath is greater than 0, right? If this is a square root, we want to make sure this is greater than or equal to 0. So logarithms, we make sure they're greater than 0. Square roots, we make sure it's greater than or equal to. Well, does the cube do anything? No, it's really just the x minus 1. So, as Sean was saying, we want to make sure it's greater than or equal to 1. And that's where we get, that's the bracket.
Greater than or equal to.
Correct, because it's a square root. Remember, it's okay to have a square root of 0,
Yeah, it's
just not negatives. Question? Yes?
Yeah. Can you just remember the top line again?
The very first one?
Not the second one.
The second one.
The next one is
So this is odd over odd, where the top is smaller. So this has a vertical tangent. Now you're going to have your calculators available to you, so you'll actually be able to see that it's kind of an S shape that's been moved to the right 6 and up 2. So you'll be able to see right at 6, you get a vertical tangent there.
so
Um,
when you have a vertical tangent, then like you look at the x minus 6.
You look at, okay, so for actually all of these, the last 3, they're all horizontal shifts. So it all depends on where it's been shifted. Or maybe it's at 0, you know. Maybe it's just an X.
And then like for the cusp in the corner, if you knew where those are, what would
Okay, so
what would you look at?
okay, so a cusp would be like 4/5. So that would be, yeah, so you can't have it equal to -5. So that would be negative infinity to -5, and then -5 to infinity.
Well, then you also write that it's a cusp, right?
Yeah, that's a cusp. Yeah, we didn't identify any of them, but these are the first one was discontinuities. This is a vertical tangent. So, yeah, actually, why don't we just look at these? These are discontinuities. I'll write that down. I asked those kind of questions in a separate part, but I think it's good to identify them here. This one is a, what did we say this one? Vertical tangent. And remember, you're going to have your notes in front of you, or hopefully while you're working on it. So you can have that page where we wrote down all that information. Or hopefully you wrote it down.
That's cool.
I think it's posted on Haiku anyway.
This is
LN?
continuous.
Yeah, this has none. This has no type, this has nothing against the differentiability. It's just differentiable on its domain. So there are no corners, there are no cusps, there's no vertical tangents, there's no discontinuities. You can draw this graph with one pen stroke. How about the next one?
Same.
Same thing. So this also has none, which is an option on the quiz. So you'll see it'll say discontinuity, cusp, corner, vertical tangent, or none. So none is an option, just so you know. Not trying to trick you.
I hate that. I always feel like you're trying to trick us.
Well, look at the difference between these. These all had like multiple parts to the intervals. What do you notice about the LN and then this one here? It just had one section to the graph. There was nothing breaking up the interval into more than one section. That should give you a clue. And then this one. Okay, now I'm going to give you, oh, what was this one? Sorry, we didn't write that down. This was a cusp. What? Okay. Okay, now I'm going to give you a couple of piecewise functions.
That's very.
Isn't that nice of me?
Very nice of you.
It's
cool
very
of you guys.
wise of you to do that.
Waka waka.
Even your dog likes you.
I don't have a dog, so shut him out.
In this case, if it's okay.
Good point.
Is it really?
You should be used to it by now.
That's Fiona. That's your real name.
What do you want us to do?
Okay, so same kind of directions. I want you to tell me where the function is differentiable.
That's what the fun of.
And then I want you to tell me if it's a, basically if you have a piecewise function, and notice I don't have any like even over odd or odd over odd powers, so I don't have any cusps or vertical tangents. So I'm just checking for discontinuity. So remember what I said, check for discontinuity first. How do I check that?
Plug in.
Okay, plug in the 0. So actually plug in 0, we get negative 1. Plug in 0, we get negative 1. So we know it's continuous. However, do we know if it's differentiable?
We in fact do
How do
not.
we know?
It's not
Okay. All right, hold on. Let's write down. So f prime, we're looking at 0. That's the one in question. From the left. What's the left-hand derivative? So remember, derivatives are slopes. Can we see from the left side of this piecewise function? We didn't put it on our calculator. It's 2. It's just that. Now, what about the derivative from the right? Oh, well, it's an x squared minus 1. So, because I can't, well, how do we know? Okay, I'm not quite sure. I can't see it. It's not an equation of a line. So I'm just going to go through the process of looking at the limit definition. So it's going to be f of x plus h, our x is 0, so it's going to be 0 plus h squared minus 1. And then minus, and then plug in 0, we get negative 1 all over h. I'm just plugging into that f of x plus h minus f of x all over h formula.
How did you get 2 for
Yeah.
Oh, it's just y equals mx plus b. So I just identified that it was an equation. If it's an equation of a line, so like I know that my left-hand derivative here is 4. Because it's mx plus, it's all I have to do. I don't need to show anywhere. What's the derivative here? Yeah, you actually get 0 because you get 2x when you're all done. Yeah, you get,
And 2 in fact.
when you're all done, you get 2h, no, not 2h. You get h squared over h. So you get h, and then you get 0. So these two derivatives from the left and from the right came out to be not equal to each other. So this is a corner. And where is it differentiable? So it's differentiable everywhere else. Everywhere else is fine. So it's going to be from negative infinity to 0, and then 0 to infinity.
Oh wait, because we're doing 0. Plug in 0. Got it.
Remember, look at the piecewise function. Look how it was defined. It was defined for values less than 0 and then greater than 0. So this is a line. So I know it has a slope everywhere except for maybe where it switches. And then this one, it's a parabola. I know it has a slope everywhere except for maybe where it had switched. Now, if these both came out to 2, then it's differentiable from negative infinity to infinity. Yes.
Okay. So this might be obvious, but for some reason I'm not understanding it. Why can we not just look before the x squared and see that its coefficient is 1?
We can't. So I could have given you a line. I actually can give you a piecewise function that's continuous and differentiable. Would you like to? I could.
For like, so for the top one we were able to do it because it's mx plus b.
Right, but
So is
the slope of a parabola is constant. It's changing constantly.
right.
So that's, depending on where I'm looking at the parabola, like if you were to trace a parabola, it has a different slope. Whereas the line 2x minus 1 is always going to have that slope of 2.
Could piecewise only be corner? Or is it going to be corner?
It could be a discontinuity. Check that one. I wanted to give you a couple of different examples, so I know I kind of gave it away, didn't I? Okay.
Yeah. Excuse my language. That's okay.
Forgiven. In the next section, I'm going to show you a shortcut so you can find the derivatives of piecewise functions like that. Unfortunately, we're not there yet. I know. There goes math. You're going to like look ahead. So, tell me, what is this continuous at 0? What happens when we plug 0 in the left? So if I just plug in 0 from the left,
Why is it not just 4?
it's it's 5.
It's confusing me.
Why isn't it 4?
Why isn't it
That makes
4?
plus B.
Yeah.
No, I'm not talking about the derivative.
Oh, you're
See,
putting it-
it's very confusing, guys. I know. I'm not trying to trick you or anything.
Oh, one's prime and one's not.
This was the derivative. This is the derivative. This is when we first did continuity in the last one. I said just plug in 0, right? And what did we get? We got -1. Plug in 0 here. We got -1. So this is really doing the same thing. I just actually wrote it out this time. Plug in 0 here. I get 5. Plug in 0 here. I get 4.
Then why-
This is the left. Remember what I said for continuity? You need the left and the right hand derivatives to match up, and the actual point.
So it's just
But
continuity.
the first one isn't works. But these questions look exactly the same. So how would you know that you did different?
Yeah.
Okay, so I really did this part here. I just didn't show it.
Yeah.
So when I said, is it continuous? I said, if you plug in 0 from the left,
Oh, you
we
did
got
that
-1.
Yeah.
And then I said, what about if you plug in 0 from the right and you plugged it in and you got -1? So check. Perfect. So we did that. I just didn't write it down. Okay, so remember how I wrote at the very top? I kind of gave you like a step 1 and step 2. I said, check for continuity. Okay? So, see here, I check for continuity first. Once I check for continuity, then I go check for all the other stuff. So here, I checked for continuity. I found out that they're not the same. I'm done. I don't have to go any further. So this is differentiable from -infinity to 0, 0 to infinity, and it is, oops, discontinuity. I feel like that seemed confusing, or let me see what else I have on here to see if we have time for more. Are you okay sketching the graph of the derivative? Like looking at the slopes and just making the little line
Am I
segments?
sketching the graph in the line?
Okay, we have time for,
With the line and the
yeah. Oh, did I move too fast?
No, I'm still a little.
You're thinking, that's why I was looking at the clock to see if I have time to do 2 more examples. Okay. I'm going to give you 2 more piecewise functions, and I'm only going to give you 2 at the most. I'm not going to give you like more than 2 pieces. All right, let's do this. Let's do 2x plus 1. Sorry, I just want to make sure it comes out.
Can we sketch the graph on our graphing calculator?
No, that won't work.
Our
Hold on.
grade for graphing calculator?
It's hard to come up with one.
Where it's differentiable.
Do I want one that's differentiable? Let me change this.
I believe in you. That's 4.
Yeah, I just also want to make sure that it's okay. Okay, got that one.
Are we doing this?
Tell me where it's differentiable, and then if it's not differentiable somewhere, what's the problem? The corner-cusp
So first you check continuity.
check continuity always. I guess I could give you even one more. There's basically three different things that could occur. You could have, with a piecewise function, you could have a corner, a discontinuity, or it could just be fine, and it could be okay everywhere. Those are your choices, which is a lot. You got 3 choices for your answer. So I basically gave you all 3 choices here. Do you want to just look at one by one?
Is the top one fine?
Okay, so let's take a look at the top one. So tell me first, is it continuous? So here's, again, this is, when I do these problems, this is my thought process. I'll say, is it continuous?
Whoa.
I know, I was trying to change the color. So I'm going to first just literally, this is not derivative yet. I'm just plugging in 1 from the left, and I'm plugging in 1 from the right. I want to get the same answer. If I don't get the same answer, then I'm done. I don't have to go any further. Sienna. All right, so what happens when we plug in 1 from the left? We get 5, and when we plug in 1 from the right, 5. Good. Now we want to check to see, is it a corner? Okay, so do you understand what I'm saying here? If you have a piecewise function and you get that it's continuous, you have to do the extra step and see, okay, I know it's continuous, now I have to check to see if it's a corner. And you could graph this on your calculator and it might be really obvious, but the definite way to find out is to do the derivative. Now, I'm always going to give you one that's a line, so it's not that difficult to do. So here, I'm looking for the derivative of 1 from the left. Well, that's an equation of a line, y equals mx plus b. So what's the derivative from the left? 2. Now what I want to do is I want to make sure the derivative from the right is also 2.
Yeah.
That one takes a little bit more work. That's going to be the limit as h approaches 0. And so we have 1 plus h squared plus 4 minus 5. Right? Because it's f of x plus h minus f of x. And remember, we're plugging in a value of 1. Now it's just a matter of FOIL. So we get 1 plus 2h plus h squared, and that'll be a minus 1 when we combine. So I get the 1's to cancel, and I get to take out an h, factor out an h, cancel the h, and we're left with 2. What does that mean?
It is.
It's fine.
It's differentiable from negative infinity to positive infinity.
I did it.
Yeah, you did.
So this one is no corner because it came out to be the same. So that's kind of our third possibility. If it's continuous and the derivatives are the same, then it's differentiable on the whole thing. Then we're good to go. So, like this next one, look, what's the first thing we checked on this one? Continuity. Is it continuous? No, why not? Because if you look at from the left, we get 4, and from the right, we get 7. So I don't have to check the derivatives. We're done. This is a discontinuity. So this is going to be from negative infinity to 2 to infinity. Oh, you know what? I meant to make this a, that should be a minus 1. Sorry. I had more for it. Okay, so the next one, 4x minus 1, 2x squared minus 1. Okay, so we check continuity. So if we look at the limit from the left, we get -1. We get a limit from the right, we get -1. So that means it's continuous. Now what do we want to check? Just like the first one on this, well, not the first one, but the one on the top of the page was, now we check for a corner. Oh, that's weird, it moved. I don't know. I know. How did that happen? So this is continuous. Now we want to check for a corner. So from the left, so the derivative from the left is 4. How about the derivative from the right?
You know,
Oh,
sometimes it's
I
gotta
think
be
I made this
different.
one come out to be the same. That's all right. No, it should come out to 0. It's 0. Because you have limit h approaches 0 from the right of 2, 0 plus h squared minus 1 minus -1. Anyway, we get 0. I know we're out of time here. So since we got 4 here and 0 here, we have a corner at x equals 0. So let me get you. Okay, here is your take home. You're going to sign the top of it,
Like
which
right now.
says, well, you're going to write your name, and then I always get a signature. Oh, your due date, if you want to put Monday, it's the 2nd.
It's already it'll be already November.
So, again, by signing below, you pledge to take this quiz honestly, and the work is your own. Not a website, not a
And then
tutor,
second semester.
not a friend.
Oh, second semester senior.
Yes, I can spell.
We're so close to being second semester.
Yeah, I know.
What?
Month and a half until finals.